Swayam Prabha. Digital India. Educated India.
Friends, welcome to the course on maritime structures under fire, blast and explosion, jointly coordinated by myself, Professor Chandrasekaran and Professor Gaurav at IIT Gandhinagar. This lecture number 2 will talk about structural action and understanding the response behavior of maritime structures under different types of loads. Just to rewind back, the different types of offshore structures, we said that the fixed type and the compliant type have a different structural forms as the depth of water they are commissioned are different. The substructural geometric form is different from a fixed type structure with that of a compliant type structure. One depends on strength to resist the loads, whereas the other depends on its compliancy, the geometric form to resist the loads. The demerit in the second form is that these structures are permitted to undergo large displacements. When they undergo large displacements, the relative displacement between the structure and the fluid water particle is the one responsible for reduction of forces acting on these structures. Let us slightly go ahead to understand more about the structural form of the rest of type of structures before we learn about the structural action. Structural forms of both compliant and floating structures are conceived based upon the primitive idea, the order of which they counteract the applied loads acting on them. Maritime structures are designed to counteract loads through innovative geometric forms, essentially not by strength but by structural properties and the geometric arrangement of the members of a structural form. So, we said this very clearly as form dominant approach in the structural design of maritime structures. Therefore, friends, rigid supported systems which are conventionally good to transfer loads to the foundation shall not be the attractive candidates for maritime structures in deep waters. So, principally we must understand that the structural design format of maritime structures in the current scenario in ultra deep waters etc. are different from the conventional designs. So, there is a difference significantly the design perspective itself, because compliant and floating structures are permitted to undergo large displacements, whereas fixed types are not. Therefore, the design perspective globally changes from its idea of strength based design to geometric based or form dominant design. Let us see which are those factors which influence the choice of the geometric form. A stable configuration is one of the primitive requirements of any geometric form. Okay? A stable configuration is very important because this will help us to reduce installation, fabrication and decommissioning cost. Geometric forms that attract lower capex, that is capital investment, leads to high return on investment. Geometric form should result in early start of production and possess very high mobility. Geometric form that requires least intervention should be one of the best candidates for maritime structures. Structures are designed to remain insensitive to lateral loads. Ideally speaking, hypothetically I want a system which does not respond or reflect to any reaction which is forced upon them by the wave and wind loads. So, the action or the lateral loads arising from wave, wind and current and earthquakes should not bother my structural form in terms of design at all. Hypothetically, that is what I want, but compliant platforms are expected to resist these loads using both the material strength and structural redundancy. Friends, please pay attention to this term redundancy. These structures are highly statically indeterminate and redundant. Okay? So, therefore, the design approach now has shifted from strength based design, which actually permits very low displacements, to form dominant design which permits large displacement. So, in principle, friends, let us compare form dominant to strength based design. Here displacements are very minimum. Here displacements are actually larger. In this design, load is resisted by strength. Okay? Here load is resisted essentially by arrangement of members. We call this as geometric form. Okay? In both cases, material may be same, but still the structural action which helps the system to counteract the loads are different. Okay? Here it is geometric form, here it is strength by material and member cross section. Therefore, we can say these structures are highly structurally redundant. Okay? Complaint platforms are allowed, they are permitted rather, to undergo large displacements, but they are position restrained using cables or tethers, because you need to hold the platform in a place to perform its operation. You cannot allow the platform keep on freely floating. Okay? Even drill ships which are used, even semi-submersibles which are used for oil and gas exploration, during the operation they are anchored to the bed using either dynamic positioning systems or other ways by which they are moved to the seabed. So, they need to stay in position at a specific geographic location if they want to perform operations such as oil and gas production, drilling, exploration drilling, etc. Okay? So, therefore, friends, complaint platforms receive the material strength which will help them to alleviate or counteract the loads, but the major contribution essentially comes from the relative displacement concept of design. Okay? However, this relative displacement cannot go to infinite value. So, you have to control the displacement within the upper limits, but still the relative displacement concept which is permitted in the design is now governing the design actually. Okay? Therefore, in summary we can say complaint platforms do not resist loads by fixing the seabed, but receive lesser loads due to their motion characteristics. So, very interesting. I do not want to resist the load, I want to receive lesser load. That is a design concept now. Okay? So, complaint platforms are position restrained by cables or tethers. These cables are high pre-axially loaded tethers which offer resistance lateral loads while counteracting the buoyancy force. Therefore, strength based design is shifted to displacement controlled design. Large displacements allowed in the design form results in necessity of recentering the capability of the platform. So, let us say what is recentering. Let us take two concepts. One, I have a structural system which is founded to seabed, let us say founded to seabed. Other one is a system which is floating but anchored to seabed. Okay. This is floating but anchored to seabed. This is fixed to seabed. Okay. Let us say I use steel as a construction material. Let me draw the stress strain curve of steel. Okay. Now, draw it again. Let us say up to this limit, I will restrict the applied stresses in the design. So, we can call this value as yield strength. Okay. You will notice that the initial portion of this remains elastic. Okay. So, it is a straight line, it remains elastic. So, we know the slope of this is called Young's modulus. Okay. So, this is elastic initially, it is a straight line, linear. So, elasticity is a property of the material which enables its original shape and size regain upon removal of load. So, let me write that elasticity is the property of the material which helps to regain its original size and shape, okay, upon removal of load. Whereas, recentering is a geometric property, rather system property. which helps to reach its equilibrium position in the presence of load. So, very interesting friends. One is in the absence, other is in the presence. One is a material property, other is a geometric property. Okay? So, this is applicable to floating structures, this is applicable to fixed structures. So, elasticity refers to material property which ensures to regain original form, shape and size upon removal of load. This is true only when the load is applied within elastic limit of the material. That is okay, that is we understand that. Recentering is an extension of this property. Recentering refers to capability of the structural form, not the material, to regain its initial position, which may not be static equilibrium position, okay, dynamic equilibrium position, in the presence of external forces, not upon the removal like elasticity. So, one happens in the presence, it is a geometric property, other happens in the absence, which is a structural property or material property. Okay? Two things are different. So, therefore, the design philosophy which is now dependent on structural action has also need to be different, they cannot be same. Okay? In the context of the design, it is very important to learn that compliant platform design permits large displacement, therefore, that should be an integral part of the design itself. Okay? Recentering enables safety existence of other appurtenances such as auxiliary fixtures, risers, pipelines, electric cables, umbilical etc., which are connected to the platform. One of the fundamental difference between the elasticity and recentering is that elasticity is material property, recentering is geometric property. So, in form dominant design, recentering becomes very important as we go ahead. So, design of geometric forms therefore, in principle is dominated by balancing the buoyancy with the weight. A preferred design is to make buoyancy exceed the weight, what we call positive buoyant systems. This can conveniently enable very easy installation, therefore, the cost of installation can be significantly less. The difference between these two forces, that is buoyancy and the weight, is compensated by axial pretension in the cables. So, tension like platform design is essentially based on this focus. Okay. Large displacements now invoke added mass presence in the body. Okay. What is added mass presence? Let us say when I have cylinder, if this be water level, this becomes a submerged volume in the cylinder. Okay. When the cylinder is moving, let us say it takes a new position like this. So, this much portion which now new is caused or causing added mass, because there is an additional submerged volume and we know the mass is now proportional to this submerged volume. So, this additional submerged volume is now adding additional mass to the floating system. So, added mass will be an additional feature which is called as variable submergence effect. Okay. This helps to restore the dynamic equilibrium of the system in the presence of forces. One of the most successful structural form of this is tensional platform. Okay. Having said this, let us move on to the structural action of different kinds of platforms. Let us say the jacket platforms. We already said jacket platforms are transparent to wave and wind action. Only the members will attract forces, but the forces will pass through the members in between the gap. Therefore, the overall attraction of forces are lesser. Okay. Platform resists the loads by stiffness and strength, not by motion. Okay, that is jacket platforms. Let us look at the load transfer path. When the load is applied onto the platform, okay, the load is caused by the wave, wind and current acting on the platform. The load has to go to the deck. From the deck it has got to the jacket legs, and from the legs it has got to the pile. Okay. Load has to go to the members and the pile. Load has to go to the members and the pile. Members and the pile. That is the load path. Okay. Axial forces actually dominate in bracings, while the legs experience axial force and bending, the combined action. Okay. So, the legs will have a combined action of axial force and bending, whereas the braces will predominantly have axial forces. Okay. Piles which are driven below will provide fixity of the legs to the seabed, and therefore, they will limit displacements. These platforms are suitable for shallow waters where structural rigidity is feasible. Let us go on to other type of platform, which is gravity based structure, which is also a fixed type, but the difference is the colossal weight of the platform is so heavy, the platform does not rest on legs or jacket legs like this, but they rest on huge solid or hollow concrete columns, okay, the bulk columns. So, this is what we call colossal weight. Huge colossal weight. So, they have concrete caissons, which have a massive concrete caissons at the bottom, you can see at the bottom. They will hold the platform down for its weight. The lateral loads acting on this platform will be resisted by the base friction and large overturning resistance offered by these caissons. The local load transfer acts through the contact pressure at the seabed. The load comes on to the caissons, and at this junction the contact pressure will be resisting the load. The large area at the base, okay, reduces bearing pressure, but the most worrying part is it increases the seabed's covering. The platform will settle because of its colossal weight. The structural action in this platform is more or less rigid and non-compliant, they do not move. Displacements are very minimum in these kinds of platforms. Let us talk about the jack-up rigs. A typical figure what you see here is a jack-up rig. This is the deck which has got all appurtenances and facilities used for oil and gas exploration. When it looks like a vessel or a ship, let us say when a jack-up rig, okay, is sailing, all these legs will be kept up. That is why called jack up. When they reach their site, when they reaches the site, let us say it travels, it reaches the site, these legs will get into water. So, this is the water level, still the water level. So, what happens is by pushing the legs inside, okay, the deck will be lifted up, that is why it is called jack up, okay, jack up platforms, and the top side contains all facilities which are very common for every offshore platform. So, jack up rigs essentially resists the loads by the foundation called spud can. Spud can looks like an inverted cone, okay. So, what happens is this leg with the spud can is pressurized into the sand or clayey soil, not on rocks. Because of suction filled in this gap, this holds the platform. Okay. So, they are fixed to the seabed using spud cans, whereas they are fixed to the seabed by their own sulphate, colossal weight, whereas these are fixed to the seabed using piles. See the foundation difference. Okay. So, when they move to the site, the platform is jacked up to the site. Once the operation is completed, then the legs are driven up like this and the platform is sailed to the next location. Okay. Vertical loads of the deck are transferred to the seabed through the legs. That is the load path. And from the legs, it goes to spud can and it goes to the soil. Spud cans provide bearing resistance and stability at the seabed. These kind of structures are stiff with minimal motion, suitable for moderate water depths, let us say varying from 250 to 400 meters. Let us talk about a compliant platform in general. Compliance means flexibility. So, this is one of the compliant platform what you see on the screen, where the substructure consists of a tower. Okay. We can also connect guy wires to the tower to resist its motion, then we call this as guide towers. Okay. Guide towers. They are designed to move with the waves rather than make them rigid. Okay. For example, if this is fixed to the seabed by hinged connection, okay, then when the platform swings because of wave action, okay, let us say I have a guy wire. When the platform moves to the right, this guy wire try to pull the platform back. When you have a guy wire here, when the platform swings to the left, this guy wire pulls the platform back. Okay. So, recentering is automatically obtained by the design. The response of the platform under these loads is controlled by flexibility and geometry. The restoring forces either come from mooring lines or guy wires or tethers and not from the self weight. Okay. Whereas, in this platform the restoring force comes from the self weight. Okay. These towers are suitable for deep and ultra deep waters. One of the compliant towers is called articulated tower, where the bottom is like a hinged connection called as articulation. Articulation is a hinged connection which is capable of rotating 360 degree like this, okay, like this, a hinged connection 360 degree, but it cannot move in any degree of freedom, only rotation is allowed. Okay, this is called articulation. The typical articulation is seen here, which is otherwise called as universal joint. Okay, this platform has two chambers called ballast chamber and buoyancy chamber. Ballast chamber improves stability, buoyancy chamber improves recentering of the platform. So, the tower is connected to the seabed using universal joint. Environmental loads acting on this will be resisted by an inverted pendulum action, like a pendulum invert. So, this keeps on dancing like this and it alleviates the loads. The buoyancy chambers on the top provide recentering capability. The ballast chambers provide the bottom improve stability. Bending moments of the seabed are minimized because there is a hinged joint here, the bending moment at this joint is practically 0. The only issue in this kind of design is this platform undergoes continuous motion. So, this hinge will be subjected to fatigue failure. So, we also have to learn about the fatigue method of design for these structures. Okay. Bending stresses are shifted away from the foundation and they are now taken away by the tower and the buoyancy section respectively. Let us talk about tension-leg platform. It is again a floating system anchored to the seabed using tethers. The design concept is buoyancy exceeds the weight. Buoyancy exceeds the weight. So, buoyancy acting downward plus T naught acting downward, buoyancy acting upward, buoyancy acting upward will be now resisted by W acting downward plus T naught acting downward. So, buoyancy exceeds the weight, therefore, the T naught, the axial tether tension balances that difference. So, excessive buoyancy is now balanced by axial pretension in the tethers. Okay. Look at the structural action. If I have a system which is connected to the seabed using tethers, axial tension in the tethers, if this is my water level which I call as still water level, when the platform moves or swings to the right, platform swings to the right, let us say, tethers will be remaining the same position. Okay. So, now the vertical component of this will add weight, the horizontal component of this will try to pull the platform back, correct. If the platform moves to the left, tethers will remain same position. If they are axially pretensioned, the vertical component adds weight, the horizontal component pulls the platform back. So, recentering is automatically done by the design. So, the shift of the original position to the new position in horizontal direction is called as offset. The shift from old to new position in the vertical direction is called as set down. So, offset happens in surge or sway degree of freedom, set down happens in heave degree of freedom. So, now I can say surge and sway degrees of freedom are strongly coupled with heave degree of freedom. So, there is a coupling motion. When you give surge motion, heave automatically occurs. When you invoke heave motion, surge automatically occurs. So, this coupling action enables recentering and this helps to counteract the forces. Okay? This is what we call as TLP mechanics. So, TLP mechanics has got vertical downward movement called set down and horizontal movement called offset. They are strongly coupled. Heave, pitch, roll and or stiff degrees of freedom, whereas surge, sway and yaw remains flexible. I think in the last lecture we discussed about the degrees of freedom. Please refer to the slide. Surge, sway and yaw are flexible degrees of freedom, whereas heave, pitch and roll are stiff degrees of freedom. So, a same structure has got both degrees of freedom combined is called an hybrid structure. So, TLPs are called hybrid platforms. Okay. Let us talk about the spar platform, single point anchor reservoir. So, spar has got a substructure different from TLP. In TLP we have only tethers, whereas in spar we have a column member, okay, which we call as a deep draft chamber. So, stability is achieved by this deep draft chamber and low center of gravity. Environmental loads are resisted through inertia and hydrostatic restoring force. Mooring system mainly provides station keeping, not stiffness, whereas here mooring system provides stiffness also. Okay. Here it only offers station keeping. Large mass on the top side leads to long natural periods. It avoids wave resonance. Structural action is dominated by global rigid body motion. Okay. So, friends, let us look at the semi-submersible platform. Semi-submersible are also one of the platforms used for oil and gas exploration. It has got reduced waterplane area, which minimizes the wave induced forces. Loads are transferred through the column members and the pontoons to the mooring system. Okay. Platform relies on hydrodynamic transparency rather than stiffness. Now, I have moved the design concept from strength based, stiffness based, material characteristic to total geometric form, which comes from the floating platforms like semi-submersibles. The load is resisted purely by hydrodynamic transparency and not by stiffness. Response is generated by the coupled heave, pitch and roll motions. Mooring lines ensure position keeping and not rigidity. But one of the important problem with this kind of structure is the fatigue because of cyclic waves in the vessel or in the drill ships. So, friends, drill ships and semi-submersibles are completely floating platforms which are anchored to the seabed using mooring lines. When you look at the method of anchoring them, let us say position keeping, we talk about let us say drill ships. So, they have thrusters in the fore and aft of the vessel. This is the direction of motion of the vessel. Okay. What happens is on the deck they have geodetic positioning system fixed. So, this is connected to the internet. So, when the platform moves, the lat and long coordinates of this point is known. Further, under the wave action, if the platform moves, this CG moves the new point, the new lat and long or latitude and longitude are known. Okay. The difference between delta x nu to delta x volt, delta y nu to delta y volt is computed and the thrusters will apply forces to push or pull the drill ship to the new position. Okay. This arrangement is what we call as dynamic positioning system, in general DPS. Okay. Sometimes drill ships are also anchored using mooring lines. Okay. They can also be used. However, to facilitate the operation of drilling, drill ships must be position restrained either using a DPS or using mooring lines. So, alternates are DPS or mooring lines. Okay. Let us look at the last one, which is a new generation platform, is a Triceratop. Interestingly friends, look at the platform. The top side has got all facilities what an offshore platform should have. For example, a drilling derrick, a crane, a helipad, a flare boom, the living quarters, accommodation, then the main deck which has electromechanical equipments, compressors, machine room, etc. Then a drilling derrick which is used to do the drilling operation. So, the top side is almost same as that of any platform. Now, the bottom has got buoyant legs which are connected to the top side using something called ball joint. Now, the advantage of the ball joint is when the platform is rotating under the wave action, the legs, this rotation will be observed by these ball joints, it will not get transferred to the deck. Under the wind action, if the platform is rotating, okay, these ball joints will observe the rotation, will not transfer to the legs. So, the moment at this connection, practically becomes 0. I will not say 0, it is equal to some value m star for which these joints are designed. Okay, they are not transferred, right. So, we can say the Triceratop is an example of partially isolated system. Why partially? Not completely, because any surge motion, any heave motion will be transferred from the leg to the deck and from the deck to the leg. So, the restriction is not done on displacement degrees, but only on rotational degrees. Therefore, I can say the superstructure is partially isolated from the substructure using ball joints. Okay. So, ball joints allow translation, but isolates rotation. The structural action of this platform essentially depends on geometry induced compliance, okay, not on rigidity. The loads acting on the platform are taken care of by the buoyant legs and the tethers. Okay. The rotational motion are decoupled. This helps to protect the deck and the risers. Geometric form results in a reduced force transmission and improved stability of the platform. These platforms are very well suitable for deep and ultra deep waters. The recent one is a regasification platform, which is again conceived on the same idea as a Triceratop. Regasification is a process which actually helps us to convert the crude oil extruded into gasoline form. You can look at the complicated topside structure available on a typical regasification platform. The whole one is called as a deck. The deck is isolated partially from the legs using hinges. The one which you see here are called buoyant legs, and the buoyant legs are free to move inward and outward. Like for example, if I have a deck and I have a buoyant leg connected by a ball joint, okay, with respect to the CG, the legs are having freedom to move or to rotate inward and outward. If they rotate too much, okay, the stress at this joint will become beyond the design of this. Therefore, they will be supported. So, what we do is we interconnect these legs by a central system, and then in this system we introduce spring mass damper. Okay. So, these passive dampers will restrict the outward swing of these legs. So, they are called response control mechanisms, which you see here. This platform also holds the CNG tank on the top, the LNG tankers on the top, then it has got a crane, helipad, living quarters, flare boom, living quarters, and also regasification unit. Okay. All these are housed on the top side of the deck, and the deck rests on the ball joints which are mutually connected between the leg and the buoyant legs. Okay. It is an example again of a classically partially isolated maritime structure. Okay. The hinge connection allows controlled inward outward movement of the buoyant legs. Therefore, the passive control helps reduce the response of the buoyant legs. Platform remains laterally compliant, but vertically restrained from motion, right. So, heave degree is rigid, but surge and sway degrees are compliant. The loads are resisted by buoyancy and tether restoring forces. So, that is what you see in this platform. So, friends, in this lecture we learnt about the structural action of various platforms, we also learned more about the form dominant design approach, we also understood how the structural design has shifted from strength based to geometric based design. There is a shift. So, the moment I say geometric based design, it allows excessive displacement. So, these displacements should be controlled. Okay. Classical most successful example of a compliant platform is a tension leg platform. We clearly understood what is TLP mechanics, how surge, sway and heave are coupled, and in this process we learnt how recentering is invoked. Then we move on to learn semi-submersibles and drill ships. So, in this we learnt about the dynamic positioning system and the mooring systems, which enables a platform to position restraint which is necessary to do offshore drilling operation. Then we moved on to advanced structures like triceratops, regasification platforms, where the superstructure is partially isolated from the substructure. Friends, one of the important merit of this platform is that this platform is now being investigated for also rocket launching for satellite communication rockets from the sea. So, since the superstructure is partially isolated, the thrust force or the recoil effect which is generated from the rocket launch does not affect the substructure. Okay. So, now there is a very interesting advanced research going on in analyzing and understanding the feasibility of using this platform or such platforms for offshore satellite launchers. So, friends, we have also learnt about advanced systems as we go ahead. So, now we learned the structural action of a fixed type, compliant and floating type. We understood that the design philosophy is different for these kind of structures. Whatever may be the load acting on them, the design philosophy must allow large displacements in its format. Okay? So, we learnt it. We will learn furthermore about the maritime structures and the types and classification and loads etc. in the next lecture as well. Thank you very much. Namaste.